In this short video, I'll introduce the chain rule in finding the derivative of functions. So the chain rule is used when you want to find the derivative of a composite functions, d over dx, f of g of x. So in these composite functions, you know that f of x, f is the outer function, and g of x is the inner function. So if you let the inner function g of x equals to u, then you can rewrite this derivative problem to d over dx of f of u. So now you have u and x are different variables. You have dx, but you have f of u. They are different variables. So then I have to look at d over dx, and I split d over dx into d over du times du over dx. So then I want to introduce the variable u in terms of the derivative, right? So now I can group d over du with f of u because they have the same variable, f of u and du, multiplied by du over dx. Okay. So d over du of f of u can be written as f prime of u, which is the derivative of f in terms of u. And du over dx will be u prime, which is the derivative of u in terms of x. And keep in mind that u is g of x, and g of x is the inner functions of the composite function f of g of x. So let's look at an example. If you given the function f of x equal to square root of 2x, then you know that this is a composite functions, where the inner functions is 2x. So you let u equals to 2x. And the outer functions is square root. But now it has to be square root of u, because you already let 2x equals to u. Right. So then you can find the derivative u prime equals to 2. And you can find the derivative f prime of u equals to 1 over 2 square root of u. Again, we need to have our variables consistent. So, and as earlier, we formulate the formula f prime of x equals to f prime of u times u prime. And we found f prime of u is 1 over 2 square root of u. We found that u prime is 2. We know that we can cancel 2 in the denominator and 2 in the numerator to get 1 over square root of u. And we're not done yet. Our functions is a function in terms of x, so we have to convert u back to x, which is u equals to 2x in this case. Then you will have 1 over square root of 2x because u equals to 2x. So the conclusion is if f of x equals to square root of 2x, then f prime of x equals to 1 over square root of 2x. Now let's look at another example. The function f of x equals to sine of x squared. And then we identify the inner function is x squared. So then we let u equal to x squared. The outer function is sine. So f of u equals to sine of u. Again, if u equals x squared, u prime is going to be 2x using the power rule. If f of u is sine of u, then f prime of u is cosine of u. Now, put everything together, f prime of x equals to f prime of u times u prime. So f prime of u is cosine of u. U prime is 2x. And then again, u equals to x squared. So you have to convert u back to x squared, which gives you cosine of x squared times 2x is the derivative of sine of x squared. Now I notice a pattern of the inner function and the outer function. So if I put the inner functions into a box, let's say this red box, and I put the outer functions into a blue box, another box, right? Let's say sine x in the blue box. So then in order to find the derivative of sine of x squared, I first find the derivative of x squared, d over dx. It's going to be 2x. And then I will find the derivative of sine in terms of the red box, d over d red box, right? Because I just want to emphasize that it's not d over dx, but the variables has to be whatever inside the red box. So you have cosine of the red box, which is cosine of x squared, which will give you the same answers that you found earlier. And eventually, I think this could be a method. It's a box method. That's what I called it. So let's look at a little more complicated functions. This is f of x is a composite function, but it has 3 different layers. Can you find the derivative of these functions? So I would take each of the layer and I put in a box. First, I have the most inner box function, which is x squared plus 2. And I have another box, which is the sine functions, a red box. And I have another box for the natural log functions, ln function. So to find the derivative of these functions, I first find the derivative of the most inner box, which is the derivative inside the blue box. It has x. It's going to be 2x, because the derivative of x squared is 2x, the derivative of 2 is 0. And then I go to the second box, the sine, the red box, right? I find the derivative of sine, but in terms of the blue box. So whatever function in the blue box, I have to use that variable. So the derivative of sine is cosine, and I keep the blue box, which is x squared plus 2. I go to the outer function, which is natural log functions. And again, I have to take the derivative of natural log, but with respect to the red box. So whatever functions inside the red box, I have to keep it with me. So the derivative of natural logs is 1 over the red box. And the function inside the red box is sine of x squared plus 2. See, I found the derivative of this little complicated function using the box method. And as you can see that, you can combine cosine and sine together to make it the derivative of f of x, f prime of x, equals to 2x times cotangent of x squared plus 2, which is the final answer. So this box methods here will help you find the derivative of composite functions in a more visual way, right? You put each of the functions into each of the layer into each of the box, and you find the derivative of each of the box with respect to whatever box is inside it. All right, have fun.